This is the fifth lecture of our topic center of mass and center of stiffness. So students, in the last lecture we are discussing about example number 5. In example number 5, there are four columns named as A, B, C, D. All the four columns having same dimension of 300 mm cross 600 mm, but the orientation of the columns are different. Say for example, you can see that in this figure, the orientation of column A and column B is horizontal. So its horizontal dimension is 600 mm, and for column C and column D the orientation is like vertical. So you can see that in the figure, if the load is acting on horizontal direction, then which columns are taking more loads? So it's a logical question and it's logic about that. If your load is acting on this direction, then whenever your load is acting on this face, the distance traveled by the load is 600 mm because this horizontal direction is 600 mm. And for this column, if the horizontal force is acting on this direction, they are passing through 300 mm dimension. So for column A, the load is traveling by 600 mm, and for column C, they are traveling by 300 mm. So which column takes more load? The simple answer is column A because they travel more loads and the load distribution is more for column A. So now let us discuss and derive why and how much load is taken by column A, B, C and D. Okay, so in the last lecture we are discussing about center of mass. So the coordinates of center of mass is 3, 2 because in the question it is clearly mentioned that uniform mass distribution. So uniform mass distribution, it means the center of mass is exact at the center point over here. And second one is center of stiffness. So center of stiffness coordinates is 3, 3.2. So you can see that this is your center of mass and this is your center of stiffness. Okay, so your center of mass and center of stiffness x coordinates is remain at the same point. You can see that this is 3. The coordinates in x direction for center of mass is 3 meter and center of stiffness is 3 meters. So your building or your system is symmetric for x axis. Now the turn is for y-axis. So you can see that your center of mass coordinate is 2 meter and center of stiffness coordinate is at 3.2 meters. So there is some distance. So what is that distance called? That distance called static eccentricity. We are already discussed in our introductory section of this topic that the distance between center of mass and center of stiffness is called static eccentricity. So now you can see that this distance is denoted by small e. Small a means static eccentricity. So whenever this load is acting at the center point, but this load is distributed over here, so there will be some moment generated. So you can see that point is acting at this point and going to this point. So there will be anti-clockwise moment because your load is acting but your load distribution is like that. So there is anti-clockwise moment generated in this system. So if you have to balance this system, so you have to couple means anti moment means in this system there are anti-clockwise moment generated, so you have to provide clockwise moment. Okay, so now let us start our example. So first of all we have to find out static eccentricity. So it is already discussed that its x coordinate is at the same point, so static eccentricity in x direction is 0 and in y direction it is minus 1.2 meter. Minus sign indicate anti-clockwise moment. So anti-clockwise moment generated, so we have to provide clockwise moment, therefore we have to design for plus 1.2 meter. Okay, so how much moment is generated? So we have to find out in the next slide. So you can see that next is design eccentricity. So in clause number 7.9.2, there are two equations of design eccentricity. The first equation 1.5 ESI. ESI means static eccentricity plus 0.05 into BI. Now you can see that 1.5 into ESI means static eccentricity. So what is the value of static eccentricity? The value is plus 1.2 meter. Now plus 0.05. Next is BI. Now what is the term BI? The term BI is floor plan dimension of floor perpendicular to the direction of wind. So our wind is acting, means our force is acting on this direction, means x direction. So our perpendicular dimension, which is y dimension. So our y dimension is of 4 meter. So the value of BI is 4. After calculating all this value, our EDI is 2 meter and second is ESI minus 0.05 into BI. So what is the value of ESI? The value of ESI is plus 1.2 minus 0.05 into the value of BI is 4. So after putting all this value, we will get our answer. First is 2 and second one is 1. But you can see that which answer is necessary. So whichever of these gives the more severe effect. Severe effect means maximum value. Okay. So we have to take design eccentricity is larger value of two value. So what is the maximum value? Maximum value is 2. So our EDI is plus 2 meter. Now we have to find out how much moment is generated in this system. So our design eccentricity is 2 and our force is 200 kilonewton. So force into perpendicular, it gives moment. So moment is force is 200 kilonewton and moment is 2 meter. So our answer is 400 kilonewton into meter. Now we have to divide or distribute these 400 kilonewton into meter moments and 200 load distributed on 4 columns. Okay, so now let us calculate with one table. So our table is first is A, B, C, A and D. 4 columns are there. Now second one is stiffness. So you all know that our system is unsymmetric in y direction because our eccentricity is minus 1.2 for y direction only. Okay. So we have to find out K and IYY. So we have to cut all the columns in y direction. So our column A is horizontal dimension. So whenever we have to cut that column in y direction, so 600 portion is cut. So what is the equation of I? I equation is BD cube by 12. So what is the value of B? The value of B is 300. The value of D is 600 cube divided by 12. So we will get our answer 5.4 into 10 raised to 9. The orientation of column A and column B is same as horizontal. So our IYY for column A and column B is remain same. Next one is for column C. So our column C is vertical column, means our 300 mm is horizontal and 600 mm is vertical. So whenever we have to cut it vertical, so our 300 portion is cut. So our equation for C column is 600 into 300 cube, because our 300 cube portion is cut. Okay, so the answer is 1.32 into 10 raised to 9, and orientation of C and D is same, so the answer remains same. Next is Ri. So this term is very most important. Ri means the distance of column and center of stiffness in y direction. I repeat, Ri means center of column and the center of stiffness. So you can see that this is plus 0.8. So how this value comes? So you can see that this is your center of stiffness in y direction. So this line is our 3.2 meter line. Our this column is from origin. From origin this distance is 4 meter. But from this distance is plus 0.8 meter. Now this is your origin. This line is your origin. Okay. So this is plus 0.8. For this in y direction it is also plus 0.8. For this it's minus 3.2, and for this it's minus 3.2. So this is our Ri. Okay. Next is KIRI. So we have to multiply column number 2 and column number 3, then we will get our answer KIRI. Next is KIRI square, which is the multiplication of column number 2 and square multiplication of column number 3. So we will get our answer of KIRI square. Okay. Next is KIRI divided by summation of KIRI square. This equation is just like distribution of base shear, in which VB into WIHI square divided by summation of WIHI square, like that. Okay, but this equation is not given in IS code provision, so you have to remember this equation. Okay, so KIRI means this 4.32 into 10 raised to 9 divided by 34.56 into 10 raised to 9. So you will get your answer 0.125. Okay. Next is 4.32 into 10 raised to 9 divided by 34.56 into 10 raised to 9. So you will get your answer 0.125. You can see that over here this sign is minus sign, so this answer is minus answer, and same this all the values is same, only change in sign. Okay, next is force due to moment. So force equation is moment into factor. So our moment is 400 kilonewton into meter. So we have to multiply this column with 400. Okay. So 400 into 0.125. So you will get your answer 50. 400 into 0.125, it is 50, minus 0.125 into 400, it is minus 50, and same way for column D. Now next column, last column is very most important, that which column takes how much load. So the equation is Fx means force, which is 200, into Ki divided by summation of Ki, means 5.4 into 10 raised to 9 divided by 13.5 into 10 raised to 9, which gives Ki upon summation of Ki into 200. So we will get our answer 80. 5.4 into 10 raised to 9 divided by 13.5 into 10 raised to 9 into 200. So you will get your answer 80. Next is 1.35 into 10 raised to 9 divided by 13.5 into 10 raised to 9 into 200. So you will get your answer 20 and same as 20. So students, as we discussed at the start of our lecture, our column orientation of column A is horizontal direction, so it takes a larger load. So you can see that in this figure your column A and column B takes more load because the width of column in the force direction is more, so it takes larger load. Okay, so this is the very most important example of this topic, center of mass and center of stiffness. So students, this is the end of this topic.